Okay, so let's continue our discussion from last time. So last time we completed our discussion of the royalty theory of the string. Now we want to discuss various projections. Okay, so we had discussed last time that there are 16 sectors in the superstring that one could look at. But only 10 of these 16 sectors, are wave level matching. The NS minus sector has half integer spaced oscillator numbers because of the minus half in the 0 point energy in the NS sector, and so it cannot be level matched with anything else. All of the other sectors have integer spaced oscillator. So we can have NS minus, NS minus, and then alpha, beta, where alpha and beta are any of NS plus or minus plus. So that's 9 plus 1, 10 to the And the question now this leaves open the possibility of having 2 to the power 10 different string theories in which each sector is either included or not. So that's 2 choices per sector, so that's 2 to the power 10. And a question you might ask is, are all these superstring theories consistent? Are some of them consistent? And so on. We're now going to try to, we're going to, in a very simple way now, address this question. Okay, so there are 3 requirements we're going to put on the spectrum of string theory. We briefly discussed these requirements last time, but I'll say it again for the camera. The first one is simply that correlation functions of all the vertex operators in the theory are simultaneously well defined. By which I mean that if you've got any a correlation function of an arbitrary number of insertions of operators, then these are well defined. If you take one of the operators around another one and come back to the same point, okay, these correlation functions are given by single valued functions. Okay, they're well defined with correlation. Okay, so an example of correlation function that is not well defined is e to the power I h, the usual Bose-Einstein fermion, where e to the power I h by 2. Because this correlator, if we work out this OPE at z at 0, we get what is it? Z to the half times normal order e to the power I h z plus h of 0. And this now has an ordinary Taylor series expansion. So it's expanded in integer power to z. But we got the z to the power half. So this correlation function, if we now take the correlator of this with e to the power I3 by h, something like that, this correlation function will have a non-integer power to z. And so it's not a single valued function of the correlator. So the correlation function is not, if you ask what is the value of the correlator when this function is put here, this function is put here, this function is put there, you don't get a single answer. There are many possible answers. In this case, 2 possible answers. That's not good enough. We want all correlations to be well defined, so they can be given by single value functions. Okay? So that is our first criteria. That if we include many different sectors, we have many different, each of them has their own vertex operator. And we want all these vertex operators to give simultaneously well defined correlations. Okay, great. Now, how do we implement that? See, any sector is either Ramond or Lebesgue. Okay, so let's invent a number eta, is it eta, nu, whatever, something like that, which is equal to 1 if it's we're in the Ramond sector, and is equal to 0 if we're in the okay? And then we've also got this quantum number associated with sectors, which is the fermion. Okay? Now, each of these is on the left moving side you're either in the Ramon sector or the Levershore sector. On the left moving side you're either positive fermion number plus or minus. Similarly the right ones. So sectors are characterized by value of nu and nu tilde. When the Ramon to Levershore is the left moving and right moving side. And F. Okay. Now, what we see, what is easy to see, we see as now, is that the phase that the question of whether operators have mutually well-defined correlation functions with each other depends only on these two things: on their fermion number and which sector. Okay, let's try to see this in an example. Okay. Let's look at the Ramon sector vertex operator in the ground state. Okay, so suppose we've got the vertex operator e to the power I h1 by 2 plus h2 by 2 h5 by 2 plus 5 by 2. Okay, now let me take any other operator, some O. Okay. That the correlation function of this guy with this guy. Okay? So now this O has some fermion number. The fermion number, remember, is just m1 plus m2 plus m3 plus m4 plus m5 plus zeta, where m1 is the coefficient behind e to the power I h1. So the operator is e to the power I m1 h1 by 2 plus e to the power m2 h2 by 2 and so on, and plus e to the power I e to the power zeta 5. Okay, fermion number is the sum of these things. Now, let's compute, if we take this operator and contract it to this guy, let's compute what overall power of z we get. What power of z we get from the exponential contractions. Okay? So, just like here we got, it's dropped out, just like here we got z to the power half with h by 2 and h. Here we're going to get z to the power half times m1 plus m2 plus m3 plus m4 plus m5 minus plus z. If you look at the contractions of the power of z that you get in the contractions because of the exponentials in this operator OP. Is this clear? Suppose you just had O, which was, so suppose O was e to the power I m1 h1 plus m2 h2 m5 plus zeta 5. Contract this with this. You get this power of z times something normal. Of course, now in addition to these exponentials, you could have del h's or things in the denominator. But those things don't give you these extra phases. Those things are all give you single value. So that's all. Okay? Now in this example you see that this quantity here, this quantity here is depending on whether this number here is even or odd. This power of z is either a whole integer or a half integer. If the power of z is a whole integer, okay, then the correlation function is going to be right. But if the power of z is a half integer, then the correlation function is not right. Right? Because you get z subtraction. But this number is simply the fermion number. Okay? So, correlation functions with this operator are single valued, provided that the fermion number of that operator is even. That is, provided that minus 1 to the power f fermion number is 1. Now, I choose a specific operator in Ramon sector. But this actually doesn't. Which operator I choose doesn't matter. Because every other operator in the Ramon sector is this plus integer multiples of this. Well, I'm sorry, I said that wrong. I said that wrong. Okay, so this is true for this operator. Okay, now suppose we're looking at something, operator, the operator product between this guy and something in the NS set. Then it doesn't matter which other state we're looking at, because everything else has integer additions to this to the units of age, and in the NS set you only have integers. Okay, so the additional things will only give you additional integer powers of z. Okay. On the other hand, if the other guy is in the Ramon sector, then you could have additional factors coming in. Okay. But we've already worked out the rule between the NS. If one of the guys is in the NS sector, the other guy is in the Ramon sector. Okay. So we get z to the power half integer if we have Ramon with NS minus. And this is not left and right. This is the first operator Ramon, the second operator NS minus. That gives us a half integer power. Okay? But not if it's Ramon with NS plus. Now, you see, if you get an integer power of z times a half integer power of z times a half integer power of z bar, that gives you an absolute value, which is very right. Okay? So, now I'm going to write down the general rule. The general rule for when you get, it's clear that you're always going to get either double value or single value correlation. So I'm going to write out the general rule for when something is double valued and when it's single valued. And we'll see if it makes sense. The general rule is this. Suppose we have the two operators which have nu1 tilde. That's, remember, 0 in the NS sector, 1 in the Ramon sector, left and right. And f1, f1. This is for O. Then there's also O2, which has nu2 tilde, f2, f2. Then, I'm claiming that the general rule is determined by this number. The relative signs are unimportant, as we see. It's nu1 f2 minus nu2 f1 minus nu1 tilde f2 tilde plus nu1 tilde. This is the thing that you have to compute. If this object is one or an odd number, you get a multi-value correlation between these two things. If this object is 0 or 2 or any of the number, you get a single value. Okay? So in the example we looked at, we ignored the right movers. Okay? And we had one object in the NS sector. So let's say number 2 was in the NS sector. So this was 0. Nu2 was 0. So this was there. And then we got nu1, which is 1 times f2. So we got 1 if the fermion number of the operator in the NS sector was 1, and 0 if it had 0 or even. Okay? You see, the point is this, let's see, it's got to be symmetric. These minus signs are put in largely for show, because if you add twice of any integer, it doesn't change the formula. So I can change this formula, this plus, this minus, the signs any odd way. It doesn't change the formula. So we're only doing 1, 2. Right? You see, we have to have this term, you see, we have to have a symmetric term. I've made it minus, you can make it plus 2, well, it doesn't matter. And then clearly the right numbers work the same way. Okay, you can just play around with various possibilities to convince yourself this is correct. You see, you can think of this contribution as the phase you get by taking this term around that operator because something because the other operator goes around this. However you want to think about it, you can convince yourself this formula is correct. Is this okay? Do you want more justification of this formula? Shall we look at more examples? Are you happy and check this out? Okay, let's see. Let me give you one more example in the Ramon sector. Okay, let's look at e to the power I h1 plus by 2 plus I2 by 2 minus h5 minus 5 by 2. Okay, this will be to the power I h1 by 2 plus I h2 by 2 with a plus h5 minus 5. Now let's compute the net powers of second. Okay? So what do we get? From this guy and this guy, we get z to the power 1/4. Right? So we get z to the 1/4. But then there are 4 such, so to the power 4. Okay? Then from this guy and this guy, we get z to the power minus 1/4. And from this guy and this guy, because there's no I, we get another z to the power. Okay? So we get integer z is ignorable, so we get 1 over z, 1 over square. Okay? But notice that this is the Ramon sector operator plus formula. Whereas this is the Ramon sector operator, minus formula. Formula number minus 1. This is the Ramon sector operator, formula number plus 1. So according to this rule, one of these is 1 while the second one is 0. So one of the two formula numbers is 0. The second one is non-zero, both into Ramon sector. So once again, we should have got a 1, that's what we get. Okay? Okay, you can play around with this and convince yourself, now you can play around with this and convince yourself that adding integers modulo 2 to this would not change this product, but that's good because it does not change this formula. Whereas integers modulo 1 to this would change this product. In particular, if you make this plus, that would change it. Clearly, an operator with itself should be well defined, and it is because it changes this z to the 1/4 by minus 1/4 to z to the 1/4 cancels this. But any odd integer added here would make this well defined, but any even integer would leave it in. Okay? But that's the same thing as saying as long as you don't change the formula number of this operator, you get the same answer. This formula number is defined. And minus 1 is formula.
Last term, then you have complex.
Right. Done. Okay. So I'll leave you to play around with this formula if you want. It's more or less obvious. I mean, play around with this easily. Okay. So we use this formula. Fine. So this is the first case. You see, this gives you a restriction on which sectors can mutually appear together. Now, there are 2 more things that we want to say. The next restriction that we have is that if any 2 operators appear in our string theory, then all operators that appear in the OP of that operator appear in that string. This is necessary for union. Okay? Because if you, as we've seen before in our discussion of the bosonic string, operators that appear in the OP of 2 operators appear as poles in space-time you get associated poles with 4-point functions. And if you had a pole with no propagating state associated with that pole, that would be finite. So we clearly want a theory in which all operators that appear in the OP of any two allowed operators also are allowed operators. Okay? So, how does that work? Suppose we've got two operators which are defined by mu1, mu1 theta, f1, and f1. If we look at the OP of this with mu2 tilde, f2 and f2 tilde, you can easily see that all operators in the OP will have quantum numbers mu1 plus mu2, mu1 tilde plus mu2 tilde, f1 plus f2, f1 tilde plus. This statement simply asserts that the OP of two operators in the Riemann sector belongs to the Lenni-Schwarz sector. This is obvious. Okay, for instance, e to the power ih by 2 with e to the power ih by 2 gives you only e to the power ih integer h's. Okay, basically half integer plus half integer is integer. That's the statement. Okay, whereas this, but if you take Riemann sector plus Lenni-Schwarz sector, you get Riemann sector. Take that's what we mean is half integer plus integer is half integer. And if you take two guys in the NS sector, you get NS sector because integer plus integer is integer. Okay? So that's an obvious statement. This part asserts that fermion number is additive, which is also obvious. Right, fermion number is conserved in the OP. So that part's also obvious. And of course it works separately for Lenni with the right. Okay? So what did we discover? You see, suppose we got two different operators with these quantum numbers, then the sector we get by adding the numbers associated with the two different operators should also exist in the thing. Otherwise you have an inconsistency. Okay. That's requirement number 2. So first requirement was well defined as a correlator. Second requirement was closure of the OP. And the third requirement, which is slightly more abstract, the one we used before, is modular invariance of the partition function. Okay. Now, modular invariance of the partition function is an interesting requirement that we're going to examine in more detail very soon. But there is something about that that I want to immediately remind you of. This we've seen many times, but let me say it intuitively. You know, suppose you've got, I want to convince you that very general considerations of modular invariance always imply that you will always have at least one Riemann sector in both the left moving and the right moving parts. But the Riemann sector must appear both in the four left movers and the right movers. It's impossible to have a modular invariance factor in which there is no Riemann sector for either left movers or right movers. Why is that? You see, if you have any sector at all, you have an NS sector. I mean, let's suppose there are no Riemann sectors. Okay? So then you have an NS sector which is minus boundary conditions, anti-periodic boundary conditions of the selection cycle. Okay? Now the boundary conditions here could be either anti-periodic or periodic. So you have some sectors, and let's say that it's either plus or minus. If it's plus, by doing the S duality flip, by taking the cycles, modular invariance makes this a Riemann sector. Because the spatial cycle will then have the positive boundary condition. That's Riemann sector. If it's minus, then something a little more subtle. Tau goes to tau plus 1. Gives you a Riemann sector. Because minus and minus is plus. Right? The boundary conditions on this cycle of the torus is plus. Because it's anti-periodic here, therefore periodic. Is this clear? Okay? And then interpreting this as a space cycle by variance. That ensures that there's a Raman cycle. This argument works both for the left movers and the right movers independently. Okay? Now we'll have many more constraints from module n there in such a simple statement. But this simple statement will allow us already to start very quickly generating all of this. Okay? So, fine. Is this clear? That there must be at least, for both the right left moving and in the right moving path, there must be at least one Raman cycle. Is this clear? Okay. Now that we have all these three conditions, it's very easy to simply try to generate all possible consistent projections. Let's do it. From modular n variance, we've seen that there must be at least one Raman sector. Let's first classify our theories into two kinds. Those that have a Raman Nebu-Schwarz sector. These are theories that in space-time will have Fermions. And those that don't. Let's start with those that do. So suppose we've got a Raman sector and the Nebu-Schwarz sector. Then from level matching, the Nebu-Schwarz sector must be plus. The Raman sector could be either plus or minus, let's suppose it's plus. So we know such a sector exists. We also know that there is at least one other sector, one sector in which the right movers are involved. Okay. Okay. So let's go ahead with this. Fine. So first we got this. Now by the OP, this OP with itself gives us what? So R plus with R plus gives us NS plus. And NS plus with NS plus gives us NS plus. So NS plus and NS plus must also. And you can easily convince yourself that these are mutually local. Correlation functions are mutually local. Okay, good. But we haven't exhausted all our information. We know that there is at least one sector with a Raman guy on the right. Now we have options. Let me suppose, to start with, that the guy on the right has Raman plus. Now what else could we have? What else could we have here? Well, let's see. Suppose here we had, so there are three possible options and let's explore. Okay, so we're making various choices and we'll come back and see what other choices we could have made after we generate. Suppose it was X plus. Then let's take this with this. The OP, firstly, is this consistent? You can check that this is consistent according to this. NS plus with R plus gives you nothing. But it's consistent because there are all fermion numbers as well. Because there are no phases. Right? This rule, if all for X was 0, just gives you no phases. This is consistent. This is a consistent possibility. And then the OP of this guy with this guy gives you R plus with R plus. All further OPs are contained. For instance, this guy gives you R plus NS plus, which is here. This guy gives you self, and so on. You can check. Okay? You can also check that well, it's clear because all fermion numbers are plus that there's no requirement for mutual interaction. This is consistent. So we appear to have solved all our conditions with this choice. We appear to have solved all our conditions with this choice. We have to check modular n variance. We have to prove modular n variance. We have to check modular n variance, but we'll do that by the end of this lecture. Okay. So this is one possibility. Now let's go back and see if we can generate more possibilities. Okay. With the same starting point, suppose we had R plus, NS plus, NS plus, NS plus, and we said there had to be at least one more R sector. Let's continue to assume that it's an R plus. But let's see if there's anything else we could put here. R plus certainly could have been, but let's see if R minus could have been put here. R minus I cannot have it. It's something that because it would not be mutually local with what? See, this, clearly with this everything is mutually local. Since this and this. This guy and this guy has no problems because both are plus. But this guy and this guy has a problem because this is minus 10 over. So this guy is not mutually local with this. Okay? So making the choice R plus here, we try NS plus, that's fine. We could have had an R plus. That's fine, it's clearly mutually local because everything is plus. But now closure of the OP generates the set. Because this guy with this guy is this guy. So we also get NS plus plus. So that choice doesn't give us anything new, it's the same. Same theory. Another way of saying it is that although here we chose R plus NS plus, we saw the words in R plus R plus. We chose R plus R plus, we get R plus NS plus. Okay? So, had we chosen R plus here, this is the only theory. What clear is this? Is this clear? Okay. But we made another choice. We have R plus NS plus, NS plus, NS plus. But here instead of choosing R plus, we could have chosen R minus. Fine. Let's choose R minus. Now what could we have had? Let's make the various possible choices. Let's try NS plus. The three choices. NS plus, R plus, R minus. Let's try NS plus. This works because this is the only minus in the game, but it always hits an NS plus. So there's no case. Okay, and now let's look at the only non-trivial OP is this guy or this guy, which will give us an R plus, R minus. The only consistency that's non-trivial is between this and this. And let's check. R minus with R minus is nothing, NS plus with R plus. Okay, so this is another choice that we have made. Number 2. Okay, now let's go back and check all of the possibilities. So once again we have this. Instead of this R minus, what else could we have put? Had we put an R plus, we just generate the same possibility again because it's here. It would be the same thing. Okay? Had we put an R minus, that would have been inconsistent. Same problem. This guy and this guy would have been counted. So there's no other choice. Okay. Something I have not done, but it's true, and I'm going to ask people, okay, is that once we got this closed set, you could have had, okay, it's closed. You could have said, okay, it's closed, but could have added other things, which would then have had maybe a larger closed set, but could have added other things and then been consistent. And it's true, but I'll leave it for you to check just because all the arguments are trivial little things that to do, that there's no other sector you could have added. Suppose you have this closed set, you're trying to add any other sector, it will be inconsistent. Either that guy with all of these, with one of these has a non-local OP, or something generated in OP. Actually, I think it's just that guy with this has not.
These are the only two possible closed sets.
How do you know that? There could have been a larger closed set in which this is a subset.
But the other part leaving this closed set, that the OP is only consistent in that part, right? These are the only two possible closed sets for which these three conditions work.
No, we've shown that these are closed sets for which there could have been a larger closed set. There could have been, let's say, six sector family, in which the OPs of these four stay within themselves, but the OPs of the other two, take you out.
Yeah, but the other two, they will be closed, of course, but they would these conditions would hold there.
No, I'm saying you have to prove it. It's true that it's never possible to ignore.
Because if we do not hold there, then we have to include that in this list of possibilities.
Whether you have to. Right, but in our construction, we haven't excluded that possibility. You see, where we stopped was we found a closed set. It satisfied all requirements, then we stopped. Okay? To be logically complete, we should check that we cannot extend this construction. It's true, but I'm not going to check it. But is it clear there's something to check?
What I was thinking that only we can extend this by combining these groups.
Why? Why?
Because
right, maybe that's true. I don't say. You can now ask. There are 6 remaining sectors. Take any one of these 6 remaining guys. Now, is it consistent with all 4 of these? And if so, what is the minimal closure of the OPs described with this chart, and is it consistent? Clearly, there's no other larger set that satisfies these questions. But I think there's something to check. Okay? But I actually, last night I sat and checked it. It's very simple to do, but it's just a time-consuming process that I don't know. Okay? So, what was the assumption we made? We made the assumption that there was a Ramon-Nebu-Schwartz sector in Africa. With that assumption, and we started with this first guy being R plus. With that assumption, I'm saying that these are the only 2 possibilities for sectors. Now, the same game you play by starting with this guy being R minus. Actually, you know physically that in the Ramon sector, plus and minus are conventional. Because it's just a choice of which you call positive, what's the way you call positive chirality and what's the way you call negative. Okay. In fact, you flip these 2 conventions by a space-time parity transform. Suppose you take one of the coordinate axes, let's say x1, take x1 to it, take x minus 1. That flips the sign of 1 gamma matrix. And therefore it flips the sign of gamma 5. So it flips chirality. Okay, so by just changing x1 minus x1, which you flipped chirality. You flipped the fermion number in the Ramon sectors, but not in anything else. Okay, so while NS plus and NS minus are physically different, R plus and R minus have no physical difference. Okay, so it should be, but anyway you can directly check, that you should be able to just everywhere here change R plus to R minus and R minus to R plus. So this is also this. It's clear, it's consistent because the only problem is related with the R sector. R sector hitting NS plus is fine. R minus hitting R minus is fine. Okay? Or you could have got R minus NS plus, NS plus, NS plus, NS plus R minus, and R minus R plus. This is also consistent as you can easily. But as we just argued, these 2 theories are related to each other by a space-time parity. So they're not different. Just the same theory expressed in different coordinates. Okay? So while these 2 theories are genuinely physically different, this and this are just the same theory with different conventions. This and this are the same theory in different conventions. to regard these as separate possibilities. Okay, and we'll deal with these two as the possibilities. Okay, so we have just listed all possible consistent sets of projections in which there exists at least one NS subset. That is, there exists space-time coordinates. Let's give this guy a name. This is what's called time to wave theory. Sorry, 2D theory. And this is what's called time to wave theory. And these two are formally relative to the same thing. Okay, so clear this. Let's leave it on. Okay. Now let's explore possibilities with no. Now let's explore possibilities with no NS subset. Okay, we know that there must be at least one Raman set here. Suppose these factors are plus here. Since there's no NSR, there must be some other R here. Let's suppose it is R plus. R plus with R plus, the OP gives us NS plus, NS plus. And actually, this is a closed state. It clearly obeys the mutual locality condition, and no further OPs. I think you are with this. This thing obeys the condition that every sector has at least one OP. But this is an example of the danger that we might have run against. While this is a closed set, it's not maximally complete. It turns out that this set is not modulated. Okay, so you can ask, can you add to it to get another closed set? Okay, so let's try adding, well, what do we want? Let's suppose we try adding R minus R minus. It's clearly fine, right? This with this gives us a minus sign, but this with this gives us a minus sign, so that's up to 0. Okay, now the OP of this with this is NS minus NS. You can easily check mutual locality, and this is a closed set. So you see, this is the kind of phenomenon we could have had in these theorems. This is a closed subset inside this larger closed set. The larger closed sets are as consistent from our rules as the smaller closed set was. And it will turn out that this guy is modular there. Well, two things to check. First, that there's no further larger set you can add to get consistency. It's true. Nothing else to do. And we will demonstrate that this guy is modular invariant. This guy is type 0. Okay? What else? We started with R plus, but we could have had an R minus. Suppose we had R plus with R minus, once again we'll generate an NS plus, of course. Okay? Once again, these two are mutually local, OPs are close, but does not modulate. So, we want to generate an R. Okay, how do we do that? Well, let's once again try NS minus. Clearly mutually local because this guy has a minus sign with this guy also has a minus sign with this, it has 0, no minus signs. The OP of this with this gives us R minus R plus. To check mutual locality, everything is nice and closed. Okay. And this will turn out to be modular invariant. This is type 0 8. Though we've not been completely exhaustive, I've tried to indicate how it could be. You do this a little more exhaustively. you find there are no other possibilities. Okay? So we have just generated all possible consistent, truncations of the theory that could possibly give us consistent string theories. Okay? And we've got 4 possibilities: type 2A theory, type 2B theory, type 0A theory, type 0B theory. Of course, here once again we can switch all R pluses to R minuses, and here all R pluses, and vice versa. Same here. That will give you theories that we're not talking as distinct for the same reasons. It will be too physically. Is this clear? Right. So, now let's look at these theories a little more. The first thing to look at to see is that this theory, type 2A theory, but let's not look at type 2B theory. Okay? What is the projection that we're imposing in type 2B? We impose the projection, so that's type 2B. The projection is minus 1 to the power of x is equal to minus 1 to the power of x. Every independently left movers and right movers have plus coordinate numbers, but otherwise they can appear in all different combinations. RNS, NSNS, NSR, RR, but everything is plus. Independent projection of left movers and right movers is the coordinate. What about type 2A theory? Minus 1 to the FL is equal to 1. So left movers are always plus. But minus 1 to the power FR is equal to minus 1 to the power B. So it's 1 in the NS sector, but minus 1 in the RR sector. Newton logic. Okay? These are the standard GSO projections. This is the way GSO thought of their projection. Okay? We got it from this other consistency point of view, but it's the same answer. These theories as we've seen before, have in them a graviton, a gravitino. The gravitino had a gauge invariance, as we've seen from the condition that the vertex operators are equal for the gravitino are equal to vertex operators plus something like that to be identical. It's gauge invariance. So it's of course very plausible that these theories will be supersymmetric, because you've got a gauge invariance associated with a spin 3/2 particle, should be supergravity. And that will be the case. Okay. Notice also that these theories do not contain the ns minus ns minus sector. The ns minus ns minus sector is the sector in which there is the tachyon. So type 2A theory and type 2B theory seem likely to, and we will show indeed do, turn out to be supersymmetric theories of space-time, and as a consequence in particular do not have the tachyon. On the other hand, these theories have no phenomenon. Because you never have an NSR or RNS sector. Okay? So they're purely, the perturbative excitations are purely, in these theories, are purely bosonic. Okay? And in particular, they always have the NS minus NS minus sector, both of them. And so they take the tachyon. So the theories whose perturbative excitation is purely bosonic, and in particular, unstable theories. They're as bad at least as the bosonic, but they're as bad as the bosonic string. Okay? So while these are good suggestions to the consistency conditions of string theory on the world sheet, like the bosonic string was, at least at first sight, they're much less interesting. Because the perturbation theory we generate using these theories will not. But the suffer from all kinds of infrared divergence is from the fact that we're doing perturbation around an unstable background, then what can you really do? Yes, and these two are logically at the same stages as the bosonic string. Perhaps a little better, some technical. That's a very good question. Not obviously, but there have been many conjectures about tachyon condensation in these theories in the bosonic string somehow leading to one or the other. But there's no clear evidence. Okay, so the answer is fullness. Okay. You see, what we've got is on the potentials, as we will see as we go along in this course, string theory is a theory with a huge space of vacuum. A vacuum are stable, or at least a metastable vacuum. These are minima of potential of string theory. There are also some maximum. Of course, there are any complicated potential surface, some minimum and some maximum. And if you search hard enough for all stationary points, you sometimes land at a maximum rather. So there is some maximum in the space of string theory, presumably. And in some sense, presumably can be connected to some well-defined minimum. But in what whether that's true clearly, and in what sense it's true, if it is true, it's not ever been convincingly written. I personally have written a paper actually, claiming for evidence that type 0A theory, tachyon condensation leads to a superstring. But honestly speaking, the evidence is not very strong. Okay. So, there are many speculations you can make about this, but it's basically hard to confirm these speculations. Okay. So,
Sorry, what do you exactly mean by tachyon condensation?
it means, suppose you've got an instability in your spectrum, then if your potential is something like this, the instability is because you're expanding around maximum. But if you excite this instability, you will roll to a minimum. So tachyon compensation is trying to follow what minimum you would roll to if you excite it. So this is an unstable point in some potential space. What is the nearest stable? That's the question. Okay, let's move on. Okay, so what about the projections to type 0 theories? The projections to type 0 theories are very simple. Let's say with this theory in particular. You see, what you have is that whatever's on the left, you also have. Okay? So the sectors you choose, on the left, you also choose on the right. Now you can say that's such a formula. A formula would be that mu is equal to mu tilde, f is equal to f tilde. That's projection. Okay, so type 0b is mu equals mu tilde, f is equal to f tilde. And type 0 is almost that. Yes. Thank you. And in 0A, you've got almost that, except that in the Ramon sectors, you've got the opposite flips. So however you say that. So if it's Ramon on one side, it's Ramon on the other. If it's NS on one side, it's NS on the other. NS sectors have the same fermion number projection, so I both plus both lines. And Ramon sectors are the opposite fermion. So you can write some formula involving mu and so on to say that. So that's what you would say. Okay, so that's the projection for type 0A. Okay, great. So now, I've given you a plausibility demonstration that these four truncations give you consistent string space. But we haven't yet quite demonstrated, because there's this one set of requirement that's been lurking in the background, the requirement of modular invariance that we haven't really changed. Okay? So now let's go ahead and change the requirement of modular invariance. Let's check that honestly for all these four theories, which closes the case that these are really consistent perturbative string theories. So for the type 2 theories, so the first thing is we want to check modular invariance of what exactly. Now the bosonic string was not very, there was no ambiguity. The thing we wanted to check modular invariance of was the torus partition function of the worldsheet conformability. But now which torus partition function? We've got all these sectors and these projections. And that's fine. So we know that we should add some torus partition functions. But with what signs? Now you might think that's a stupid question, but it's not a stupid question, and let's ask the physical question that will answer this question. We'll see that in this function. You see, where does a torus partition function appear in string? It appears in, for instance, the calculation of vacuum energy, or one loop with operator insertions, completing one loop graphs there. And how does it appear? So let's try to set up first vacuum energy calculation, because everything we say for vacuum energy will also work for scattering energy. It's easier to think of. Let's try to set up the vacuum energy. Vacuum energy calculation, you remember we had a lovely interpretation of it that we were discussing in some string. It went this way. The sum over all the particles of string theory. And then, for these particles, okay, let's give a sort of hand-waving derivation. For each particle that's bosonic, you compute integral of d n p log of p squared. Because that's the one loop amplitude for a bosonic free particle of mass m. Just find the diagram. Just bubble. If it's fermionic, you do the same thing, but with a minus sign. Because fermion loops have a minus sign. Okay, so we write -1 to the power f space time. That's what the S is. And you compute this for every particle, and that's your partition function. That's vacuum energy, more or less. This one modification string there. More or less, that's the vacuum energy. Now that's sum sum. So the first thing we did previously, if you remember, was to take this log and write it as integral log of p squared plus x squared. It's written as integral d tau by tau e to the power minus p squared plus m squared. The whole thing divided by tau. This is a formula representation of log. There's some blah blah blah. This is actually divergent. Some regulators, but this gives you the log once you regulate. Okay, and then the next thing we process this one more step. I'm not sure if I leave this for a second, but there was also an identity that said that this object, this d10p, and then this object, this was the difference. So now we want this d10p, d10p, and this, I'm not sure we need it, but anyway, it's true. This is the same as d tau by tau e to the power minus x dot squared plus m squared over periodic orbits of length tau. Yeah, we will need this. Over periodic orbits of length tau, 0 tau periodicity. Suppose this is dx. Right, if you do this path integral, this is quantum mechanics, you get this. This is the part. Just one minute. What do I mean here? Sorry. Okay. I don't want to do that. Let's guess that this is equal to this. So this beta by tau is not. Yeah. Both these are true formulas, so I'm just trying to decide which one is coming. Sorry, is it confusing that this is equal to this? We may not even need it, but let me just. This is just a formula of quantum mechanics. This quantity is the partition function of quantum mechanical system. That's right. This quantity is the partition function of quantum mechanical system. Free particle, non-relativistic free particle at temperature 1 over T. But that partition function amateur did that was like this. This vector is b squared plus n squared. Okay, and energy times temperature over all density of states. So these two things are the same thing. This is Lagrangian versus Hamiltonian formulation of the same partition function. What do I actually need? I'm getting confused with where my tau is. That's what I'm just. Maybe I'm going to change the tau. Okay, sorry. This is good. Do I want to call this tau 1 over tau? That's what I want. Really, I want to call it tau 1. Tau normally relates to the surface.
I think I'm beta.
Huh? No, the formula is correct. It's just a question of what is useful for connecting the straight line.
The formula has the tau expression the first time.
Oh, you say that it's correct if this is here?
Yeah.
No. Yeah, you're right. No, wait. Yeah, you're right. Okay. This is 1 over, tau is 1 over the temperature, and tau is, thank you. E to the power minus e by t. Right? Partition function is exponential e to the power minus e by t. Thank you. Okay, that's your property. Okay, so there's a tau here, and this is equal to this. Thank you, everyone. Okay, now we didn't need. This is a mnemonic. I didn't need it. Sorry for bringing this up. Forget it. Okay, this is true. Okay, so then we write this as integral d tau by tau, then we've got this d10 t to the power minus t squared times tau. That gives you some function of tau. Yeah, we get some power and tau and so on. And then we get sum over all particles e to the power plus m squared tau, or minus m squared tau. Now minus m squared, remember, was in some, including some appropriate alpha primes and so on, was the worldsheet Hamilton. Was the eigenvalue of the worldsheet Hamilton. Okay, so this was replaced by S0 plus S0. And the sum over particles is just tracing over all oscillator states of the worldsheet Hamilton. Now to impose a constraint, we have to impose that L0 is equal to L0. And we did that, if you remember, by changing this integral over tau to an integral over d2 tau and integrating over the imaginary part. Because that gives you a Lagrange multiplier that fixes L0 is equal to L0. Okay? So, in the end, we got tau times z CFT of q to the power L0, q bar, bar L0 bar. I'm being schematic here, but it's steps are missing. Okay, that's what we got last time. But the important thing I want to keep track of is that there is that minus 1 to the fermion number, minus 1 to the fermion S. So that tells us that when in doing all this, we have to weight all states in the normal sector with a minus 1. Okay, so partition function, the partition function that we compute should have a factor minus 1 to the power mu plus mu tilde. Is this clear? Because that's the way we're going to get the object that we wanted to compute in space time. This one loop determinant in space time should have a factor of an extra factor of minus 1 for space time fermions. Space time goes on shifting. So if you have minus 1 to the power mu plus mu tilde, that will do it. Okay? Is this clear? Good. So, the thing for which we want to check modular invariance in the for the type 2 theories is the following. Let me work it out for okay. So in the type 2 theories it's very simple because left movers and right movers are just products. The projection you make on left movers is independent of the right projection you make on right. So let's deal with the sector basically. So let's look at the chiral sector and let's say type 2B theory. Think with everything projected plus. All fermion numbers are plus. So what is the projection, what is the partition function we want to get? First is the NS, which is minus, and the ordinary partition function would have a minus, yeah? And then we want to project onto minus 1 to the power f is equal to 1. Now, what you would think is that we must do this. That will project onto minus 1 to the power f because this plus change inserts the projection of an additional minus 1 to the power f. And this is correct if you deal with both the theory with both ghosts as well as matter fields. But remember that the ghosts generally what they end up doing is just killing two of the transverse equations. But in the case of the fermions, there's one more effect that the ghosts have. They add a unit of minus 1 to the vacuum, to the fermion number of the vacuum. Remember, we imposed the projection minus 1 to the power f is equal to 1, which turned into the projection minus 1 to the power f is equal to minus 1 on just matter sector. Because the ghost vacuum had minus 1 to the power f equals to minus 1. Remember, the e to the power 5 over x. So if we work this purely in terms of the matter sector, the net effect of all of that to change the cluster limits. Is this clear? Is this clear? Let me say it again. The projection we want to impose is fermion number is equal to plus 1 on host plus 1. But there is a way of thinking of the spectrum of the theory. Well, if you do the partition function over hosts, it cancels the partition function over two matter fields, transverse matter fields, except that the host vacuum has fermion number equals minus 1. Okay? So it does that. It does a cancellation, but gives you an extra minus sign for minus 1. So it changes this to this. That's clear, right? I mean, it's clear practically speaking. We dealt with minus 1 to the power x is equal to 1, and yet we had an odd number of fermion vertex operators. Yeah, the thing that satisfied minus 1 to the power f equal to 1 had a single psi field on the vacuum. Because the host vacuum had minus 1. So that's what I'm saying. If you deal just with the matter, that's equivalent to the projection minus 1 to the power f is minus 1. Okay? This is for the NS. And then we have to get minus of half. Okay? Then there are wrong signs. So plus, minus, and then plus, plus. Whether this is plus or minus, we don't really care, because that's the chirality projection. Which chirality we keep behind? Each of these will appear in our constructions. Okay? So the partition function of the world sheet theory, in particular just of the 8 components of the matter fields, because now we're taking the atomic forces. Okay? The 8 bosons and fermions, this partition function for both sides, plus and minus, should be modular invariant, at least covariant. I'll explain that. So this is the thing we want to do. Is this clear? Okay. Now, there's something interesting. As we will see, this thing will turn out to be modular, have nice modular module, essentially modular invariant. That is, its mod square or appropriate thing will be modular invariant. But would have worked have we not to this minus? Now, this minus sign, what was its origin? The origin was that came from the fact that space-time fermions contribute to one of the determinants of the minus sign. So, modular invariance of string theory forces string statistics. So, forces space-time fermions to contribute to the minus, to be anti-invariant. You see, there's some connection appearing out of two apparently completely disparate things. We motivated this structure from physics. But if there's another way, you could have got it, in fact, this is the way it's originally got. Searching for the only thing that could be modular there, and then trying to interpret it. This is the only thing that's modular there, and it looks funny at first if you've got a minus sign. Partition functions generally don't come in the vacuum with a minus sign. But it's a correct thing from space-time if you have the space statistics connection. There's if fermions acting between things. Okay? So there's some nice connection appearing between two apparently disparate mathematical structures. First, basically it's encoding the consistency structure. Okay. Questions or comments about this? Otherwise I start now exploring this partition function in mathematics. Okay. Let's explore. Any questions or comments about this? Let's try to explore this partition function more. Unfortunately, there is a talk at 4 o'clock. We should schedule it for 4:30. We don't get anywhere with this course, right? I must have taught 50 lectures and we're still. We need to move faster. But I mean, you want me to skip details? If I skip details, we move faster, but I get the feeling that won't work. Yeah, so let's just keep going. We have a year to go. Let's see where we go. We have a year to go before the first of you graduates. Okay. Then we can keep going after that. Okay, great. So let's keep moving. Okay. So now, let's see. So, if you just open your notes on the partition function of the bosonic theory, you will see that the end result of all this blah 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 was make us d2 tau by time square z CFT of the x's. This is function of tau. You know, what's this blah blah blah? This part came from the zero mode part of the x CFT. There was some tau that you had to put somewhere. Well, with an even tau squared problem. Thank you. ZCFT of the x's times ZCFT. Now we also get the ZCFT of the fermions. Where by ZCFT of the fermions means the x's is just common outside everything else. But for the fermions we need. So this is the kind of thing that we'll be examining. This combination, as we argued about before, was modular invariant. This is modular invariant, so as we should talk about, this thing is by itself got to be modular invariant. So it'll be nice and modular invariant function. So the thing that we want to check is the modular invariance of this. Now, how do we analyze this problem? Actually, it's possible to analyze this in very nice and physical way. So let's do that. We've got 8 fermions. I'm going to group them up into 2. I'm going to say something quite general actually. So let's but it's probably not going to happen this class. So let me group them up into 2 complex, in 4 pairs of complex sets. And let's study, instead of, we're studying fermions with boundary conditions plus and minus, and fermions with this -1 to the RF is equal to 1 or -1. So we can actually enlarge this problem. It will prove useful to later, for 10 lectures down the line. So let's study this enlarged problem later. And the enlarged problem is we study determinant of fermions. So we group these fermions into psi and psi bar, the 2 pairs, and we bosonize these fermions. And when we study these fermions with the boundary condition that psi of sigma plus 2 pi is equal to minus psi times e to the power I alpha and phi. But alpha is closely related to nu. Yeah, exactly. Alpha is basically nu. But alpha is nu. Alpha is nu, but it's going to be allowed to be not just 1 times tau. Yes, tau.